got to do something about that mic.
No, it's following you.
Oh, okay. I'm going to come over here. I'll come over here. I'm going to hide now. Whoa, too far. All right. I have a boundary of here. You, all here, stop me. Good idea. Perfect. Okay. I don't know where to go now. I'm going to... But I have to go to the computer. All right. I have a clicky thingy.
All right, we ready to start? Beautiful. I didn't do it. Okay. All right, well, good afternoon, everybody, and welcome. I have the very, very distinct pleasure to introduce my good friend, Shannon. Shannon and I share a lot of passions, a lot of loves, you could say. Astronomy, GLPA, working with students. We are also in a very exclusive club that we really hope that no one else joins. And that's really the only one that we don't want anybody else to join. Yeah. We are in the club of Breaking a Bone in Chile. So please, I just didn't want her to be by herself in that club.
Thanks, Sarah.
So we are together in that, but please, no one else. We're not taking any members. We're just going to keep it at just the two of us.
We promise we're inclusive, except for that one. Oh. All
what?
right.
But it wasn't in Chile. It was right after.
All right.
Okay. So, good. You can be an honorary member.
Yeah.
Okay. But with no more delay, Dr. Shannon Schmoll with the Astronomy Update.
Thank you, Sarah. All right. Are you ready to be updated? Yeah. Woo! All right. Also, show of hands. Oh, no. No. How did that happen? I didn't do that. Show of hands. Who in here is a Star Trek fan, Trekkie, Trekker, anything like that? All right, good. Most of you will get most of my references in. All right, so I don't know why I'm so into Star Trek right now, but the best of humanity. All right, so what I always start off with is a rapid fire of some news stories this year, and I have them in different categories. So first is, yay, finally, Riker and Troy finally got married. Okay. But Sunny Williams and Butch Wilmore did safely make it back home to Earth and are on solid ground. Last update, they were still in their unexpected extended stay at the Hotel ISS, but they are now back home. Also, yay, finally, on the bottom here, what's that? Ruben! All right, I am so excited about Ruben finally being online. I've been hearing about this observatory and how it's going to revolutionize astronomy since I was a freshman in college over 20 years ago. So I'm so excited to see it finally come to fruition. And they are in commissioning now, so they are testing all the pipelines and cameras and all of that, and we'll start having all of the great science data out soon. The next category. So that happened. Any Voyager fans will know what that's referencing. So first off, Katy Perry went to space. She went with 5 other women on a suborbital flight with Blue Origin. It did start a big discussion online for about a week around who's going, whether or not it's a joyride, things like that. But a lot of the stuff got directed at Katy Perry there. But that was a sort of moment this year. Also, down on the bottom there, new to me this year, we apparently have black moons. So this, first I heard was when a reporter emailed me and said, hey, what can you tell me about this? And I was like, I don't know. So apparently, if we have 2 new moons in a month, that is a black moon, much like we have blue moons with the full moons. So, apparently 2016. So this is a thing I just heard about this year. So I'm going to put this in the bucket of teachable moments with the public. So when that comes up, we can talk about all of that, I guess. All right. Next, the category is fascinating, which is Vulcan for, oh, cool. So we have a 3rd interstellar comet that has come through our solar system. Woo! It's not aliens. Okay. That is also part of the category of so that happened, which is there was a professor who was like, it could be aliens, because the orbital plane is really close to the solar system's plane. But it is our 3rd one, and it's not that we're just suddenly getting more. It's just we're getting really good at figuring out what they are now. So we're going to start getting more data to be able to understand these other objects from the universe, from the galaxy, up close in a way that we wouldn't normally be able to study them. And we have a new image of M87 from the Event Horizon Telescope, which is really cool. It looks really similar to that first one we got, except the light polarization and how that light's coming out is changing really rapidly. It's changed a lot in those few years. And so this is going to help us understand the rate at which these things are changing near the black hole and how that might be able to help us understand how jets form, which is still kind of like a mystery. So that's exciting. Another category here is the Ad Astra category here of, I want to take a moment to remember Fred Espenak and Jim Lovell. We all know Fred Espenak as Mr. Eclipse, and he has done a lot of work on calculating eclipses, popularizing them, resources, and information that I know everyone in this room has probably used, and we will continue to use for a long time. And then also Jim Lovell, who is probably best known as the commander of Apollo 13, and played by Tom Hanks. So. But he was very instrumental in the early space program. He served on Gemini 7 and 12 and was on Apollo 8, which was the first mission that went to the moon and orbited it. So Ad Astra to them. And then we have one more. Where's the elephant? There's a member of the Elephant Today family. Thank you. It's really a woolly mammoth, so thank you. Oh, Sally. Can you open the tag and tell me what its name is? Monty Money. Can everyone say hi, Monty? Hi, Monty. Thank you. We have now addressed the elephant in the room. Thank you. Also, this is now a tradition because the 2nd year in a row I bought a prop at the gift shop of our host for FT. All right, we got to talk funding. So in the US, it is not outside of the realm of update for me to talk about new missions or telescopes or anything like that. But all of those come with funding. And a lot of that funding comes from the US government, not exclusively, and we're going to also talk about that. But let's talk mostly, there's just been so many news stories. I want to take a moment to actually kind of distill down what's been going on with science funding in the US as it relates to astronomy and astronomy research and facilities. And the main funders of astronomy research and facilities in the US is the National Science Foundation and NASA. So we're going to focus in on those. I've got 3 categories. I like categorizing things and color coding them, so there you go. We're going to talk about staffing at the agencies, we're going to talk about grant terminations, and we're going to talk about budgets. And I'll try to make this fast so we can get to the good stuff, okay? So first, staffing, we have seen significant cuts at both NSF and NASA. So at NSF, they normally would have about 2,100 staff members. 1,700 are permanent staff. 400 are permanent positions, but the people who are in them rotate out every 2 to 4 years. That's to keep where NSF is at sort of the cutting edge. That's the reasoning. At this point, 466 people have left NSF, mostly through layoffs, and that's about 22% of the staff. Most of those are rotators or senior executive levels, which is a certain level of the civil service of the federal government. And I think we're going to be seeing some restructuring happening at NSF. At NASA, there was about 18,000 people. We're down nearly 4,000, so another 20% there. Again, mostly these senior executive levels working on various missions and a lot of folks have left through the deferred resignation program, which is a fancy layoff. Next is funding terminations, grant terminations. So there's a lot of numbers floating around out there when it comes to this, so I just kind of want to clarify some of them because I wanted to clarify them for me, and so I spent a lot of time with data. So trust data, not lore. Okay, so at NSF, that's where a lot of the grant terminations happened. I know there's some people in this room who have been part of those grants that were terminated. So up at the top there, that's the total number. 1,700 is what's in most news stories, but there's been more since then. So this is from grantwitness.org, which has been tracking all of these. So it's about just under 2,000 grants have been terminated, which are worth about $1.7 billion. Of those, 13 or so, 11 to 13, depending on how you count it, were astronomy grants, which was worth about $5.1 million. And the reason for the termination from NSF on their FAQ page is the awards that are not aligned with program goals or agency priorities have been terminated, including but not limited to those on DEI, environmental justice, and misinformation. So these are the reasons why they're saying they are terminating it. It is normal for NSF to change their priorities when there's a new administration. It's just moving forward, all of the new grants they issue align with those priorities. It is not normal for them to go back and cancel already awarded and contracted grants that are active. So because of that, there have been many legal challenges to this. So the number that you see up here in the parentheses, 620, that's the number that are possibly reinstated from those legal challenges. That just means that there is an order from a judge to reinstate it. It's not clear if it's actually been reinstated by NSF yet. What I also want to point out here is we see these numbers like 1.7 or $1.4 billion. That's the total value of that grant that was awarded when they had their proposal accepted. These are multi-year grants, though. These go from 2 to 5 years usually. So what you see in parentheses is what was left unspent. So this is the amount that was actually left over that was canceled. These projects were in the middle of running for the most part, though. So for astronomy grants, that was about $2.2 million left unspent. And what I wanted to show here is just from NSF, these are the different directorates here, so you can see that relative impact. So in orange, that is the total number of grants given in 2024 by that area of NSF. In teal is the number that were canceled or terminated in 2025. The numbers are all different years and everything, so it's not like a direct comparison, but it's a relative idea. So you can see most of them were in education and social sciences. MPS is math and physical sciences. That's where astronomical sciences are housed, just to see a relative hit here. At NASA, it's all astronomy, so I'm not going to split that out. We've seen things like this. $420 million worth of contracts were canceled at NASA. But Casey Dreyer from the Planetary Society has been going through the budget office at the federal level to actually try to find, Bob, you're here. Hi. Sorry. So like, it's Bob. We've been seeing that, but Casey Dreyer's been going through the actual budget office, and they found only about $126 million worth of grants that are actually canceled, of which only $24 million was left unspent. So this is more context for the numbers that you are seeing in the headlines. Maybe that was too deep of a dive, but I like numbers. So. Okay. Thank you. And then when it comes to the budgets, we're going to focus on the facilities. So NSF and NASA fund research grants. But They also fund some of our large facilities that astronomers use, like Rubin. And so these are the proposed budgets, first NSF and then we'll look at NASA, that are aligned with what the White House wants. These are not formalized. These are not adopted budgets, to be clear. These are only proposed. But looking at the NSF budget, we would see about a 40% cut for LIGO, for instance. NRAO, so the National Radio Astronomy Observatory, is about 35. Green Bank specifically would be nearly 70%. Gemini would be about 40. One thing I'll point out, oh, and IceCube down here, about 50%. That's in Antarctica. Rubin, it's about to go online. This was expected, gets an 80% bump. So that's good for Rubin. But I do want to point out that NOIR Lab here, which manages our mid-scale observatories, so these are a lot of the ones that we have in Chile, on Cerro Tololo and Cerro Pachón and Kitt Peak. They also manage the data center for Rubin, which would have a nearly 75% cut. If these are adopted, NASA is not much different. You see a slight bump for human exploration. Otherwise, we are between 25 and 50% for most other operations at NASA, including science. So when we see the news articles right now that are like, people at NASA are being told to find a plan to decommission this mission or to cancel that mission or anything like that, this is in preparation for if this budget is adopted. The thing is, Congress has the power of the purse. So if Congress decides to fund, these, this is how it's supposed to work. If Congress decides to fund these at higher levels or at previous levels, then that money goes to the agencies and these can still happen and those cuts wouldn't be this drastic. Currently, we have no budget, so, you know. When we eventually have a budget, these can get to higher levels. Some earlier versions of those budgets that were being worked on before the shutdown did put us at higher levels comparable to 2024. So these are proposed, and so keep that in mind when you're looking at all of this. Most of this stuff in the budget is not set in stone yet. Okay? So here's the thing about science, okay, and funding, and the way I sort of approach this year. NSF and NASA are not the only places in the world that are funding astronomy. Even if they were to completely go away, we're still going to have astronomy research and we're going to have astronomy facilities. We are still going to have people who care about and wonder and want to look at space. But the US funds about 30 to 40% of the world's basic research, across all areas. And science isn't just pockets and bubble universes of discovery, all right? We all are interwoven with one another. It is a tapestry of science. So if you start pulling threads out of that tapestry, you might end up as a science officer and not a captain. Or what we see in the picture we are building in our science without those threads is going to look different and it's going to get built up more slowly. So yes, we will always have science and it's not going to be like the end of astronomy research. And at the same time, there is a significant portion of work that's done through funding from NSF and NASA. So all the papers that I am presenting today, I first went into something called the Web of Science, which is a fun website full of data. And you can go in there and sort by topic area. You can go in there and you can filter by the funder. So I was able to go find highly cited papers that were very foundational within the different sub-areas that were funded by NSF or NASA, and then find papers that cited them this past year and had popular news articles on them. So every one of these papers I'm presenting has been built upon research funded by NSF or NASA. But I also went through the references of every paper. And you're going to see a percentage at the start of each story. That's the percentage of the references for that paper that were funded at least partially by NSF or NASA. So you can see that percentage. Also, to make sure I wasn't being biased this year, I did go through every other astronomy update paper and do the same thing because I'm a nerd. And it's the same, very similar numbers, so. Okay, so. Fun will now commence. Let's go talk some science. Now that we're done talking about the elephant, who is very cute, so if you do, if after that you're like, I really need to hug something, please, get the elephant. Or a member of the Elephant Today family in there, over there. Okay. Ready? Moon. We like the moon because it is close to us, but not as much as a spoon because that's used for eating soup. Does anyone remember that? Thank you. Yes, but it started off from a different website, but it was part of a Quiznos commercial at one point. Okay, so we're going to talk about the moon. There's that number up in the upper right corner there. So we're talking microbes. All right. Thank you. Microbes. All right, so we send things from Earth out to other places. We have microbes on Earth. I don't know if you knew that. Ideally, we don't send the microbes and leave them there because if we find them later, we want to be like, this is from the moon and not from us. Also, if it's a place where it could survive, we don't want to contaminate that. So there's been studies before around how long can microbes survive. So generally, not very long on the moon, which is good. So we're not going to end up with a Tribble situation, okay? We don't want that. And with spacecraft, we can clean them pretty well. What we can't clean, like microbes off completely, though, is us. So when we send humans there, we really do need to know how long they survive. For the most part, we don't expect microbes to be able to survive on the moon to like reproduce and grow or anything like that. But their spores can survive for longer periods of time and remain viable. So that's what we're really trying to figure out is how long do those spores remain viable. So first, there's these different phases. The first one is ultraviolet light. It's really good at killing a lot of stuff really fast. We've been seeing that a lot since COVID. So it's going to destroy most of them like immediately, within minutes. But phase 2, this is a slower process for anything that UV doesn't kill. Excuse me. And this is coming from high surface temperatures and vacuum effects sort of working together. In the sunny parts of the moon, it's going to get pretty hot, and there's a vacuum effect. Those things work together to kill them off pretty quick. And within 1 lunar month or 1 lunation, they're all dead. Yay, I guess. Except that was because that assumed the moon was nice and smooth. Is the moon nice and smooth? No. Dave Weigel showed us that yesterday. It's not, right? And near the poles especially, there are these permanently shadowed craters where the microbes might be a little happier. And then we don't want to end up with a Tribble situation. So the thing is, it's hard to, they're permanently shadowed because there's no direct sunlight, but it doesn't mean there's no photons that reach there. So you have to understand how the light scatters on the surface into these craters, and you want to know how hot they get. Are they cold? Are they hot? What are the temperature ranges? Then you can use that information to actually figure out how long they'd survive here. And so that work was finally done a couple years ago for that UV scattering. And so using a model then, they looked at the bioburden and how long it takes to go to 0, which is a fun word. And they tested it out with using this guy, Bacillus subtilis. There he goes. He needs a little face. Okay. So they wanted to test this out with Shackleton and Faustini because these are both been listed as possible places for human exploration. And what they found based off of the UV scattering, that phase 1, the fast one, would take between 4 and 5 years for the fast stuff, and then about another 26 years after that for about 30 to 31 years total for that bioburden to go down to 0 in the permanently shadowed craters. And that sort of second phase would be only vacuum effects. It is too cold to matter. The heat isn't, the temperature is not going to contribute much because it's pretty cold there. So this is a really short one, but it's cool, and this is something we're going to need to think about when we send humans to the moon. What are the protocols we're going to have in order to make sure that we're not going to contaminate the moon? Okay. Mars. We're going to be in the solar system for a bit. Okay. Because so the thing is, I did end up with way more stories than I can fit into a talk as usual. So the final decision is the ones I like. So we went to Jezero Crater, right? We like it. Why did we go there? Thank you. What you said. No, so there's like these cool sedimentary rocks and delta formations that suggest that there used to be water there. That's why we got really excited. There's evidence of clays, which is hydrated rocks, which means water in the past. And we sent Percy there to go wander around, and you can again ask Dave where it is today. So this is why we went there. What we also saw when looking at the different satellite images were evidence of igneous rocks. So volcanoes. Who doesn't love volcanoes? Who loves volcanoes? My daughter would be so happy. Okay. So the question was also, are there some volcanoes nearby? Let's go check these out. Well, are there volcanoes nearby? I want you to look at this picture. All right, ready? Are you sure? There's also one right on the rim on the right. Right here. Well, I guess, it depends on which. Here, that's a volcano. Maybe. We have to find out. But there is a mountain there, that's for sure. It's 2 kilometers taller than everything else around it. So it's like, you shift your perspective. The garlic in the soup pretending to be potato. Or you shift your phase so you can find your missing crew members who disappeared on a transporter accident. Also a great episode of Star Trek. Okay. So this has been named Jezero Mons, so it's a mountain. So this is a new mountain. Hooray! That's cool. Now, is it a volcano? And if it is a volcano, how old is it? That's important. So these were the questions. These were some of the possibilities that it could be. It could be a shield volcano. So you have lava, it flows out, it cools down, and you build up your mountain layer by layer. Mud volcano, it's not a true volcano. But it happens similarly, except you have pressure pushing mud out at some point, and you build up a mountain that way. Could be a pedestal crater. So this is an impact crater, but you end up with really high sides instead, and all of the ejecta sort of ends up on the surface going in more of a cone shape. Or a composite volcano. So you've got lava, you have pyroclastic flows, you have ash, you have, for lack of a better term. So let's go look at there. So they used high-rise data from the Mars Reconnaissance Orbiter to study this area a little bit more closely. And what they found is this is one side of that mountain. Here's another view from over top, and you can look down on one side there. There's evidence of pyroxene and olivine, which are generally associated with igneous rocks and volcanoes, so that's exciting. But they also see clay there in the bedrock, so there seems to be pyroxene and more igneous rocks on top of the clay, which suggests at least part of the mountain is younger than the clay that's there. But it's also down one side, so maybe that was from a flow. They also measured the thermal inertia, which is how well the rock can hold on to the heat. And so ash doesn't do that very well, so you have a low thermal inertia, and they found some areas that are consistent with ash as well. And there seems to be a lot of different layering between the igneous rocks and the clay and all of that stuff, so maybe some sort of complicated history. So now we really do want to understand, one, is all of the volcanic rock from this mountain? One. Two, was it there at the same time as everything else and the water in particular? Why do we care about that? Well, this is a phase diagram of water. Okay, so on Mars today, this is the range of atmospheric pressure. On Mars today, this is the range of temperatures, and where it meets up is here, where it's purple. My favorite color. Who else likes purple? It's a good color. All right, but you can see they line up in an area that's mostly either solid, so ice, or vapor, so water vapor. Not much of it overlaps with liquids, okay? So this is why we don't really have liquid water on Mars. But we used to have a thicker atmosphere, and it used to be warmer, so we had liquid water in the past. But if we're in the era where all of this stuff was sort of going, like moving away, we're losing the atmosphere, that temperature is going down, that pressure is going down. If we had a heat source like a volcano near some water, maybe that area could have held on to that water longer, and if there was life, maybe there could have been more of it. Who knows? So that's why we care. So to answer the age question, the mountain itself is sort of on the border of what you can use crater dating for. But crater dating is, if you have a surface on your planet and it's older, that means it's been exposed to more meteors. It's been exposed to more impacts. So the more impacts you have, the older the surface. And you are also going to get more of the small ones than of the big ones. And so you can count those up to help you figure out the age. So that's what they did over here. And what they found is these are the counts that they got of the craters of different ages. These are the biggest ones to the smaller ones. There were more smaller ones. But if you take just the bigger ones, that lines up with about 1 billion years old. But there's way fewer smaller ones than you would expect for 1 billion years old, which suggests that there's some kind of erosion happening. Because the smaller ones, if you're eroding it over time, those are the first ones to go away. So what this is telling us is that 1 billion years old is like the youngest limit for this mountain. It could be older. We don't know how dynamic this area is. So it's at least 1 billion years old, could be more. But you compare that to these other regions that have subigneous rock, known as Seta and Mars, which is over near where Percy has been driving around. And you find that Mars is about 1.4 to 3.5 billion years old, and Seta is about 3.8 to 3.5 billion years old. So there's some overlap. We don't know exactly how much, but there is a complicated history here that we'd like to try to unravel. And to do that, what we really need is a sample return mission. So hopefully that'll happen. So the samples are there. They're waiting for us. But this is, I think this is an example of things are way more interesting than we thought they were going to be when we got there. Just like, all right, hold on. We'll come back to that. So anyway, in the end, it's probably not a shield volcano. The aspect ratio isn't right. It's a lot pointier than a shield volcano tends to be. Likely not a mud volcano. Those tend to be much smaller. Likely not a pedestal crater. They don't have erosion to the extent that they are seeing with this mountain. And we did see ash, and it's the right aspect ratio and size, and you compare it to Earth-based composite volcanoes, and it looks very similar. So likely this Jezero Mons is a composite volcano. So volcano! Thank you. We can all go, let's erupt with joy. Thank you. All right, now, about missions being way cooler than we thought they would be. Now we can go over here. Okay. All right, so Enceladus. Okay, sorry, still more solar system. Yes, we heart it. So we sent Cassini to Saturn. We were like, let's go look at Saturn. We're going to check out the rings. We're going to send something to land on Titan because that's a really cool moon there. And while we're there, we'll visit the others. And then we're like, oh, there's these cool plumes on Enceladus. Let's fly through them and try to figure out what they're made out of. And we're like, whoa, Enceladus is way cooler than we thought. We should have planned for this. So we didn't get like all the data we really needed, but we got a lot of really cool information. We just didn't know we needed it. So this is what we understand about Enceladus after Cassini. It used gravimetric reading. So you hear that word in Star Trek, it's real. Okay? So you use sort of different gravity measurements at different points. That helps you understand the general density and structure inside. So what we generally understand about Enceladus is that there is this icy crust, and then underneath there's a global ocean is what we expect. And we've been able to, and from that global ocean through fissures in that ice, we get these plumes, and then we try to measure stuff about the ocean from those plumes. Not to scale. Okay. And what they have generally found is trying to figure out the pH. This is something that we really want to understand is the pH of the ocean. How acidic or how basic is it? Because that's going to tell us information by like what can survive. Could be life that we're talking about, but can also just be different types of minerals and elements and things like that. So generally, the measurements based off of ratios of different things we have found in those plumes is between 8 and 12, which is a wide range. The consensus has been landing on about 8 to 9 in recent years with various studies. So regardless, you're basic. Except, but wait, we have now found phosphates in these plumes. Phosphates are exciting, okay? They are like the omega particle. Thank you. Thank you. This is a very rare particle that like triggers like a really important like study by any captain who senses it, okay? It's a big deal. All right, so phosphates are really important. We see them on Earth. They're really important for life. We talk about them in our soils because it helps our plants grow. It makes up DNA and RNA. That stuff's important. So this is really exciting, and we generally don't see it anywhere else but Earth. So using the phosphate ratios that they were able to measure there, this would actually, if it were an ideal solution of just the phosphates, it would put us around a pH of 12. So something much more basic than the current consensus. Okay? So what they did is they're like, well, it's not just the phosphates. We have all these other salt species that we have found along the way. So now let's build out a full model that includes all of these salts because they're all going to interact differently. And they took like sort of the ranges that have been measured for each of those and made the salt-rich one. So, you know, like Bones, he's real salty. All right? And I did ask several people, I'm like, who would you say is the saltiest Star Trek character? Bones. But then they also took, you know, the lower end of that and made the salt-poor version. So that's Data. He doesn't even understand what salty is. Until later. Okay. And Spot, because, okay. We are not going to recite the ode to Spot right now, just so you know. So what they did is then they took that and said, okay, if these are all the salt species we have, these are the ranges of pHs we could have, what would that then give us for a ratio of the phosphates, and then what falls into the observed range of phosphates, and you get about 10.1 to 11.6. Okay? So again, still more basic. Not 12, but more basic than we've been measuring. Okay. Except, wait, there's more. This is the plumes, okay? But those plumes are coming out of the ocean through walls of ice. So it's coming through cracks, which means all of this liquid water from the ocean comes up through very cold walls, and then there's condensation. If anyone lives in an apartment with really poor insulation, you would have that in the wintertime. So you would end up having some of that water condense back down, and that's going to release some carbon dioxide out of it, which can change the pH, and it's going to change the relative ratios. So the question is, how much? Does it really change it by that much, or is it a really significant change, and can we then estimate what the ocean itself is? Oh, I have a button. Okay. No. Too far. Okay. So what they did is they made many, many models with different amounts of carbon dioxide in there, along with different initial ocean pHs, and then evolved it through that process of coming out, and then compared it to the best estimates that we have for the amounts of carbon dioxide in that water, and found that that initial pH of about 10 or so, and that initial range is still about the right one. So it seems that what we're measuring is likely what the ocean is or very close to it. But who knows what we're going to find next. So this is an ongoing project where we're constantly building upon other people's work. Okay. But what this also means, it's not all Star Trek. So one of the things that we have seen in these plumes is silica. Okay, and we're like, ooh, silica. Because where do we see silica on Earth? One of the places is from hydrothermal vents. So as the stuff from Earth comes up and hits the really cold ocean, it sort of distills the silica out. Now, the range of pH that we are seeing here of that 10.1 to 11.6, The lower end of that is just at the top end of what silica would be able to survive in without dissolving. So this makes it harder to explain the silica through hydrothermal vents. It's not impossible, but it means that people might want to start considering other sources of that silica that we see, and not just hydrothermal vents, even though we really want it to be, because that means, extremophiles, tardigrades, things like that. All right, ready? We're finally moving out of the solar system. Okay. We're going to talk about triple stars. All right? I think this one's really cool. I'm really excited about this one. Okay, so stars. We know a lot about stars, don't we? Who here knows about stars? Who here loves stars? Yay, stars. Okay, so we have a pretty good, okay, beep. Okay. We have a pretty good handle on stars. We understand nucleosynthesis in their cores. We understand that bigger stars are hotter and they don't live as long because they run through their fuel faster to hold them up against gravity. We understand that if we plot all of them on this, what's this called? Yes, the Hertzsprung-Russell diagram. So this is temperature versus luminosity, all right? So intrinsic brightness. So if we plot all the stars on here, main sequences where stars are burning their hydrogen to their helium in their core, and that's 90% of their life. Eventually they run out of stuff in their core and they start to evolve, and they'll evolve into the red giant phase, and then they'll move around, and then the less than 8 solar mass stars end up with their cores at white dwarfs that cool off. Most of our stars are going to be in that 1 to 8 solar mass range. So we have a pretty good sense of stars when they are an individual, like 7 of 9. But most stars are part of some kind of collective, okay? And that complicates things. And so a lot of stars are born in families of binaries or triples or quadruples or quintuples and so on. But a lot of the stars do end up in triple systems, particularly this one right here. Okay. This is called a hierarchical triple, and that word is really hard to say. But this is essentially you have an inner binary system that orbit around each other, and then that acts as a single object that then orbits in a binary with a outer star, a tertiary star. So outer star, inner binary, okay? And so there's been a lot of work with these to see if what's going on with them could explain some of the weird stars that we see. And generally, that inner binary, some of the time, will merge, okay? Oh, no. Imagine that hierarchical triple over there, and the binary merges into one thing, much like Tuvix on another transporter accident. Seriously, how can you say these are safe? This is Neelix and Tuvok combined into one person named Tuvix. And unlike Janeway, we can't separate them out. Okay. Any Voyager fans? Thank you. Okay, so this is now a new binary system. And so what they wanted to do was try to understand if these sort of hierarchical triple systems that have stars merge could explain some of the weird stuff. Now, in a binary, you can get mergers when one of the stars starts to puff up into its red giant phase, and it's close enough that it kind of shares its envelope with the other star, and all of that kind of brings them in together, and they get cozy, and then they become one star. But with that third star, it kind of tugs on them and can get them to merge without that common envelope, so there's more mergers in those particular systems. So this team wanted to make a simulation of these hierarchical triples to try to see what comes out of it. And so what they did is they had a bucket of stars. This is the initial mass function. So we can measure how many stars of different sizes do we have in a given population, focusing on solar masses of 1 to 8, again, those most common ones. So you have a bucket there, and you pick out from that bucket, bloop, 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 kind of at random, what your stars are. Then you also have a similar function that describes the types of orbital periods you would have in this system. And so they did 2 different versions. The first one is they just picked out 2 randomly from that function of the orbital periods. and said the big one is that outer star, the smaller one is that inner binary. And if it was stable, they kept it. If it wasn't, they got kicked off the ship. Okay, the other one was the outer binary ruled. So what they did is they picked out one, said you are now the outer binary orbit, and now we're going to take a second bucket of the only possible stable ones and then pick out another one for you. And this simulates different possible formation histories. This would be you form a binary and along the way you capture another star versus all three are born together and that third star kind of forces the inner binary into something stable. And they just wanted to test out these different formations. They also did a version where it added in white dwarf kicks. So when a star turns into a white dwarf, part of that process is losing its layers. And if it loses its layers in one direction more than another, it can give it a little push or a little kick in one direction. And this has been thought as a possibility because we see white dwarfs near the edges of clusters and they didn't sink into the middle of clusters. And so we're like, how did they get there? So this is one idea. So they tried it with and without those white dwarf kicks. And what's unique about this particular one is they added in all the stellar evolution stuff too. What happens if all the stars are evolving the way that they should? And that's going to change things along the way. What they found is between about 55 to 60% of these triple systems end up with a merged binary. And then they looked at the types. So you ended up with ones that merged that were two main sequence stars. Or maybe it was two white dwarf stars. Or two red giants, or a red giant and a white dwarf. So they had all of those different types in there, and they found. Also, some of them were double mergers. So it's like the nesting dolls of bloop, bloop. Sound effects. Yay, thank you. Okay. So these are, I'm going to look at a couple of the weird systems that they wanted to see if this explained. One is a double white dwarf system, particularly where these white dwarfs are on a really wide orbit from one another. And you have a larger one and you have a smaller one. So when all the stars are born in a big old cluster and all together, presumably they're about the same age. So if you take the total age of these stars, they should be about the same. And so first you have your main sequence lifetime. How long are you burning that hydrogen to helium on your core before you start to evolve? And then you have your white dwarf cooling time. So larger white dwarfs will come from larger stars, and they're going to end up as a white dwarf first, and they're going to cool more slowly. So depending on what temperature you measure and the size that you have, that will tell you how old this white dwarf is. You add that to its main sequence age, you have your total age. And you do that with this one as well, with the smaller one. And that should match, except sometimes about 21 to 36% of the time, that larger one is actually younger than the smaller one for the white dwarf. So their ages don't match up. It doesn't work. So why? Could it be one of them is a merged binary? Well, they're like, yeah, sure, let's go look at that. And so they looked at what they ended up with in their simulation. They found all the double white dwarf systems that came out of it. And then they used the data that their simulation calculated to calculate those ages. Sure enough, they found some that had the discrepant ages, much like in the data. So this is showing Gaia data of those white dwarf systems. So in the red square here, that's all down here, that's the Gaia data. This is what's hard to observe up there. Against the simulation data in the blue circles, and they were able to recreate pretty much all the ones that they could see and then some. They also wanted to try it out with the distribution of orbital periods and semi-major axes of the double white dwarf systems. And they could generally recreate it, but the one with the independent periods where they just kind of picked two out of the bucket with white dwarf kicks was a lot closer than anything else. So that was sort of support for that white dwarf kick idea. All right, blue stragglers, much like the ensign kins. All right, who was an ensign for way too long. All right, so if we plot an HR diagram of a cluster of stars, all of those stars were born again at roughly the same time as the expectation. And since larger stars start to evolve first, you won't see them on the main sequence anymore. They'll have moved somewhere off. And then as that cluster gets older, that point, that turn-off point, moves down along the way. So here, this is the turn-off point with these smaller stars, but we still have some of these bluer stars, bigger stars, still on the main sequence. How weird. They're straggling behind. They're not evolving in rank. So what's going on with these? Well, they're 2 to 4 times more likely to have a companion, so to be in a double star system. They're more likely to have these really wide orbits, and they're also more likely to have some barium in them, some extra barium. Okay. So what they think is maybe going on is that if you have 2 main sequence stars or a main sequence and a red giant star that merge in that inner binary, you now have a new main sequence star that's bigger and bluer, and now it still has hydrogen in its core to continue moving along before it falls off. So it is going to be straggling behind everything else. And then also, if it happens to be a red giant with a main sequence, guess where we get barium from? The red giants. So that's where that barium would be coming from. So they tested that out as well, and they were generally able to recreate that. It's not as close as some of the other stuff, because there are certain assumptions you do have to make in a simulation. So there's more work to be done here, but they were able to recreate quite a few of the observations of these blue stragglers, which is pretty cool and exciting. All right, so moving on, last one. How am I on time? I have no idea. Oh, I have 7 minutes. Okay. All right, so fast radio bursts. It's super fast. My daughter's, like, one of her favorite dinosaurs, which I'm blanking on the name right now. It's her favorite one. Oh, it's a Gallimimus. Okay. You know why it's her favorite? Super fast. That's how she describes it. It's super fast. Okay. So we're going to talk about fast radio bursts. Alana's like, how do I photograph this? All right. See? They're super fast. All right, so these are really mysterious things that we don't fully understand what they are. We have some ideas, but much like everyone's favorite former Cardassian spy / Taylor on Deep Space Nine, we don't really know what's going on. Okay. So we know that these are coming from some kind of compact object, probably with a magnetic field. What we don't know is that coming from really close to the surface, or is it coming from some sort of shock wave phenomenon farther out? And we kind of need to figure that out to try to narrow down where these come from. They were first observed in 2007. They last on the order of micro to milliseconds. So super fast. Okay? So how do we figure that out? Because these are really bright. They're usually in other galaxies, and they outshine the other galaxy. Well, we use twinkling. All right? So we all know about star twinkling, right? Yeah, stars twinkle. What? Wow. What about planets? Yes. We might say planets don't twinkle. They don't twinkle as much. So we're gonna talk about that more in depth than what I would normally say in a show. All right, so if we're kind of close to something and we can actually see it resolved on our sky, so it has an angular size like a planet, you can imagine that the light coming out from an object is coming out as a sphere all around it, and the farther out you go, the bigger that sphere. So for us, for that particular object, we're seeing it on that sphere for like basically more of the curvature here. So you can imagine different rays of light. You'd have to fill them in here, but we're going to simplify. You can imagine you have different rays of light that are more or less coming in parallel to one another. So what you're seeing is a ray of light here and here and here. Versus if you have something that's much farther away, by the time it gets to you, it's just a very, very small portion of that sphere. It's essentially a straight line to you. So all of that light, any light you see is coming in and all together, all parallel, all in sync with one another. And so that's going to look like a point versus many points all grouped together. So when that hits our atmosphere, it's going to refract, it's going to move around. We're going to see different images of that point. So for a star, it's a point, and that image is going to bounce around inside some area on our sky. Not big area, but like a small area, right? Like we don't see Sirius going like boop, boop, boop. We see it going boop, boop, boop. Okay. So if you have a planet, on the other hand, all of those rays will also be doing the same thing. It's just that light is still within the area of the planet. And that's why we don't see it sort of jumping off or away from the object we are looking at, so we don't see it twinkling. Some does. That's why there is some twinkling, all right? And what this does is it just makes it look a little blurry to us, but we can still see it. So that's twinkling. This is all happening over time when we are watching it. But guess what? What? Fast radio bursts twinkle too. Twinkle, twinkle, little FRB. All right. Okay. They twinkle too, but it's more, because it's so fast, it's less of a time thing like we would normally observe, but it's a similar phenomenon here. So when that fast radio burst happens, as that light comes out, eventually it will go through some sort of cloud of gas. Now the scales we are talking about for distance means that those clouds of gas are really, really thin, so we estimate it as a sheet, some sort of scattering sheet. All right, so if all of this light is, pretend it's all one ray, it's all coming together, all in phase, but we still have different wavelengths of light. So that's going to cause some wavelengths of light to slow down. Others can go through just fine. Some will scatter, and that might stretch out the image. So what you end up seeing is some image broadening. You will see time delays in the radio signal, so you'll get some of those initial wavelengths immediately, but as time goes on, because some get slowed down, you'll get the rest in sort of this delayed fashion, and you get an interesting shape to your pulse. And because you're essentially getting different images on top of each other, you can end up with interference patterns as well over different wavelengths of light. Now, the time delay and the range of frequencies that this affects are directly related to one another. Because if you have multiple rays like this, it's going to cancel each other out in a similar way. You're going to end up with like some of the shorter wavelengths making it through just fine, and so you still see that, and you don't see that time delay over as many wavelengths of light. Okay, so you can look at that. You can look at that image interference. You can look at those time delays, and you can see you can kind of estimate the amount of twinkling. Okay, here's the problem. They're far away in other galaxies. They're in galaxies far, far away, one might say. Oops, wrong one. All right. So what that means, though, is you're going to have multiple sheets. You can have a lot of sheets. In general, what's going to likely affect it the most is one within the host galaxy and then one within the Milky Way. But you will ultimately see two different ones. So if you see that time delay and this range of frequencies it's affecting, they should match up if you try to solve for the other one. And when they don't, that's a sign that it's multiple ones. All right, we'll come back to that modulation index bit. All right, so what they did is they looked at this FRB 2022-1022A. Okay, great name. All right, and what they did is they were able to take that data and figure out two separate twinkling sheets here. So one that would twinkled over 128 kilohertz worth of light, one that was about 6 kilohertz of light. And they found modulation indexes, which is just a way of saying, how twinkly is it? So if it's a point source, it would be 1. If it's a really extended source, it would be 0. You wouldn't really be seeing any twinkling. And so that gives you a sense of just how extended or how wide the object is relative to that sheet. So essentially, that's going to give you a distance constraint. Okay, so with 1, the 6 kilohertz, that's a modulation index of 1.2, and with in errors and stuff, it's about 1. And then this one is just a little bit less, which suggests that it's slightly extended relative, so it's a little less twinkly relative to that sheet. So now, which one's the Milky Way? And which one's the host galaxy? So they looked at like how it varied over time, and were able to say, I honestly can't quite figure that one out. But they were able to figure out that this one was the one that was closer. And they also swapped it just in case, and the results just were worse. So likely what we have here is this one is closer, that sheet is closer to the object. All right, so that's helpful, except we still don't know if this is a smaller sheet that's closer to an object or if it's a bigger thing that's happening in that galaxy over a longer area with a sheet that's much farther out. That we have to figure out now as well. And so what they did is they figured it out. All right, if it's this twinkly and it's about this size, then the sheet has to be this big and this far out from the object. And if you do that, the sheet has to be outside the galaxy. If you swap which one is which, it's even farther out. So it's unreasonably far out from the galaxy to be the thing that is causing the twinkling, which means it has to be the closer one. And then based on how much twinkling, you can estimate just how far out it could get. And they found it was about 10,000 kilometers. That's like 5,000 miles. So that's like smaller than Earth. It's smaller than an Earth away from where it came from, which suggests to us that this is something that's happening close to the FRB. Okay, this is the first time we were able to do that. One thing that helped me a lot was a paper that came out later that was like, all right, guys, this is how we are going to go ahead and go through every possible scenario and what we're going to see with the twinkling. And it was really, really helpful. So I think we're going to see this used more to get more constraints on these FRBs. All right. Question? All right. Also, bonus points, what is Picard saying in this particular picture? Thank you. This is when he starts quoting Shakespeare and saying, "Shall I compare thee to a summer's day?" to Ferengi in order to get them to let Lixwana Troy go so he can rescue her from them. Okay, it's a good episode. All of them is. That's not true either. All right, so questions. Yeah, Chris.
Do we need the mic?
Oh, yes, the mic, please. Thank you. Oh, and hold on. I will listen and hydrate. Hydration. We're working on the mic. DS9. Voyager. Yes.
Wow.
Lower decks. Woo! I'm excited to rewatch it now that I've seen more Star Trek.
Well,
Oh, Strange New Worlds.
okay, so I was going to ask a question, but that
All
wasn't
right,
my
now
question.
let's go.
Do I use a mic? So thank you.
Okay. What is that?
No, sorry. No, I had another question besides do I use a mic. Back on your Enceladus slide, and I don't know if you have the answer to this, it just dawned from your slide. The southern fissures, we always see at least in the current pictures, with the geysers on the southern fissures, and I was thinking about tidal forces, which are squeezing the planet, and how it would, flex that ice sheet. Is there any reason or physical reason why those fissures are on the South Pole typically, as opposed to all around the ice crust? Why only the southern pole are we seeing these fissures? Or maybe, and if you don't know, I'd ask you.
My answer is I don't know. We should all be comfortable to say I don't know when we don't know.
So there's a physical reason. Okay.
I think there's also evidence for in the past having been on the North Pole. I don't remember though.
Okay, because you think about like a tidal force tennis ball, squeeze, it should be at the equator, shouldn't it?
With the other moon.
It squeezes this way.
Oh,
All right. So the answer is there is some sort of physical reason, and maybe it was possibly on the North Pole, but we'll discuss this further later in the ready room. 10 forward. All right, 10 forward. Yes.
So this is a sci-fi related but sci-fact opinion for Dr. Shannon. How many have seen The Expanse? That's quite a few, but not
Unless we're
enough.
talking
Come on,
about
let's.
Enterprise.
Okay, The Expanse, and all the way through. Okay, now, as we consider the future of humanity or whatever, AI, human forms in space, how realistic perhaps is The Expanse where we continue to stratify, you know, the miners and the controllers and the extractionists and then those who live in space without gravity as, you know, scoliosis. What do you think about The Expanse thing?
I haven't. I will answer that with, I don't know. I haven't actually seen it yet. I probably should. I will be honest, like outside of like some things like Star Trek, if it's sci-fi, it feels like work sometimes. Yeah. I'm like, I want to go back and watch Parks and Rec again or something. So I will go watch it now so I can answer that later.
How many love the Persian grandmother that runs the solar system? All right.
Now, there is a region called the Expanse in Enterprise where they go find the Xindi after they attack the Earth. So I can talk about that too. I'm watching all of Star Trek. Yes. Oh, sorry. Hi, Mindy.
Hi. This may also be an I don't know, but with the microbes, and we're worried about them on the moon, do you know if there are studies, I mean, we have microbes on our body that are beneficial, and what about those dying off, and long space travel, and whether or not we're going to be healthy?
So this is part of a much larger question around those things because we do need our microbes. So the concern is, I think with this particular study, more like making sure we don't leave our microbes behind. Like, and so that goes into things like suit design to make sure that we're not leaving stuff behind. And also trying to understand that even if we do, how long do they survive? But that is part of the question, and also keeping humans healthy along the way. So all of this is helpful to understand, like, how does this interact? So to make sure that we are being responsible, that's the hope of all of this. So that's all part of it, I guess, is the answer. Yeah, a lot of the studies I have seen, and there might be other ones as well, like I know that there's been some on like how long, we know some information of what was on the spacecraft that have gone to the moon, so how long would they have lasted? But also all the astronauts have gone to the parts where it's really nice and bright and it's not gonna last long. But this is all part of a general understanding of how all of this is gonna interact. How that works like explicitly with stuff on our bodies, if we're walking around, I'm not sure, but it's a whole thing. Back there.
All right, what are your approaches when a hot new paper drops and then...
Hold on.
Hi.
Thank you.
When a hot new paper drops and then like people start making news articles and YouTube videos about it, and people come in with who are super excited about this. They're like, oh my God, there's probably life on Mars. But don't necessarily have the background to deal with the nitty gritty of it and want to talk to you about it. What is your approach when there's like a lot of excitement about new discoveries that are very cool and very big, but also have a wider context?
So like if someone comes into my dome and asks me like, what's this thing about the new Life on Mars paper? Yeah. And I'm like, I haven't read it yet, which happened at this conference. So for me in general, if I don't know that much about it yet, or like I have like a general inkling, I'll mirror the excitement because I'm just gonna be me and I'm gonna be excited because I'm your space friend. So that's from Renee's talk today. So I think it can be like, this is really cool and exciting, but this is also preliminary, or it's part of a larger thing that we're gonna try. So I might go into a little bit more about just how the science is done and how it builds upon each other, and how it'll be interesting to see what else comes out of it, and how follow-up studies are. So it is exciting, and it's also a good chance to remind all of ourselves that, like, anytime that we see a news article like, there's life on Mars, it's like, there's maybe life on Mars. We're going to continue to study it. This is part of the thing that we are building upon, and it's that idea of all science is building upon it. And if people have questions or are wondering about it, especially if it's someone younger or earlier in their career, I can be like, if you have those questions, you can continue to investigate that as well. But I will always be like, science is a cool process. It's a process.
All right. Well, with that, we kept you over for a few minutes, but we have nothing else to get to except for the Bell Museum, so it was definitely worth it to spend a little bit more time with Shannon. Let's all thank Shannon. And here's your thank you. You get your mammoth back. All right, well, buses circulate to the Bell starting at 2:15. You can get there right away or take some time to get ready, but definitely be there by 4 for the Constellation Shootout or by 5 for the kickoff for the reception. And also, there are extra snacks on the table. Take those. They're part of your conference package, so we don't want to leave them for the hotel folks to pick them. You guys grab them.